So last time we talked about the first, basically 2/3 of the notes, and I'm going to do these with my other AP Chemistry class tomorrow, but they're a day behind, so they're going to watch the second half as homework. So you guys have to supply them with good questions, since they're going to be watching the video at home, not the live version. All right? So it's up to you, the fine people. Yeah, even you. Yeah, sorry. So what did we talk about last time? We talked about what the heck equilibrium was. We talked about how really it's a forward reaction rate and a reverse reaction rate from the last chapter about rate laws, and how if the two rates are equal, then the two equations are equal to each other. And if you have a constant divided by a constant, you get a new constant, which is where our entire rate law equation came from. We discussed that wow, there you go. That's dizzying. We discussed that this here and this here are both on the equation sheet, that the basic idea, the law of mass action, the idea that we always write the products over reactants is this kind of universally accepted chemistry perspective, so that when we look at a constant, we always understand that a rate equilibrium constant is written from a products over reactants perspective. Where did these superscripts come from? They are the coefficients. So you look at the equation, you grab the coefficient, that becomes an exponent. Eventually we talked about solids and liquids. We'll get there in a second. Then we said, hey, what if there's numbers? We could plug numbers in and solve for a constant. Why did I circle the 25 degrees Celsius there? Yes, you in the striped shirt. Yeah. The constant is don't forget that. The constant is temperature dependent. So just like when rate equals K was temperature dependent, and then there were some values there. K was temperature dependent. This is a similar concept, that K is temperature dependent. So guess what we're probably going to do at all times, though? Going to maintain the same temperature for that reaction. If the temperature changes, you have to calculate a new K, or it just has to be handed to you like a gift. And then number 3, we had to solve for the hydroiodic acid using something called algebra. If we write the reaction reverse, then the K is inverted. We also looked at the equation from a pressure perspective, and it's still products over reactants. They just kind of change some of the symbols a little bit, which I think is a little bit lame, but my opinion doesn't matter to anyone. So you shook your head yes at that. You're not supposed to shake your head yes. You're like, yeah, no one does care about your opinion. So these are all from a pressure perspective. It works the exact same. If you're really into like obscure equations, there is an equation that connects Kc and Kp. We don't use it, but there's one that connects the two that deals with the change in moles and stuff. I feel like I should have done 2 seconds of research. This is not it at all. But you have to do like the change in moles and all this other stuff. Well, the only reason I'm even writing this up here is I want to make it clear that the K for pressure and the K for concentration are not actually equal. There's an equation to make them equal, but I don't want any of you to kind of go, I had Kp, isn't that the same as Kc? Kc and the sunshine band, that's from a molarity perspective. Molarity, all right? Kp is from a pressure perspective. So someone did some fancy stuff like PV equals nRT and made molarity, moles per volume, and pressure, PV equals nRT. They kind of merged them together to make one crazy equation. All right. Then we started talking about solids. What was different about solids? What do we do with solids and equilibrium expressions? They don't count, so we replace them with a 1. There's 0 order impact, and so they have 0 order impact on the reaction rate, and if they're 0 order, then whatever the quantity is gets raised to the 0, which means it's equal to 1. I've always equated this to the fact that solids typically aren't moving unless they're flying at you. And so they don't really, you're allowed to laugh at that. It was kind of, thanks. I was just trying to hide. They always get replaced with a 1 because they're not mobile compared to the other things. Gases move at hundreds of meters per second. Solids don't, or you should duck if they do. So the same thing occurs with water. We replace water with a 1 as well. That one is for reasons I can't quite explain. I'm just going to click next. Then we got to this concept of, well, what if we're not at equilibrium? So K is at equilibrium. What if we're not there? There must be some mathematical way of measuring it. Of course there is. We call this Q. Q is the reaction quotient. It's the exact same equation, but Q could have 1,000 different answers because you're not at equilibrium. But a reaction should be moving in that direction if all the chemicals are mixed together and the conditions are right. And what you can kind of do is if you know K, and that's what I have down here in purple. Why did my voice crack? I'm not sure. If K is 40 but Q is 30, and I usually say Q is right now, K is in the future. K is when you get to balance. So are we at equilibrium? Is Q and K equal? They are not equal. So it's going to continue to react faster in one direction than the other direction. Do we need to increase the amount of products or the amount of reactants to make them equal? Products. So if I need to increase the amount of products, that means the rate forward, the rate towards the products, is currently greater than the reaction in the reverse. So if I need to increase the products, then the rate forward is currently greater than the rate in the reverse direction. And as they get closer and closer together, the two reaction rates are going to become closer and closer together, and then it's going to reach equilibrium, and it's going to appear to stop. Here's a big key thing, though, because this is a constant trick question about reaction rates and equilibrium. If you've reached equilibrium, has the reaction necessarily stopped? No, it hasn't stopped. It's just the exchange forward and the exchange backward is now in balance. It hasn't stopped. It's still occurring. That's not always true. There are some reactions that go 100% forward and the reverse reaction doesn't exist, so it only goes one direction. So you could go all the way to the products and it could stop. But in a truly reversible reaction, it doesn't stop. It just kind of keeps balancing back and forth. Then we looked at values and discussed, which way would it shift, which way would it shift, which way would it shift. In some cases, I gave you Q's, and you could think about comparing it to K. In other scenarios, you had to calculate Q after plugging in values. And then thinking about it. Today we're going to discuss Le Chatelier's principle. We didn't discuss that last time. Le Chatelier was all about, there's too many reactants, it's got to shift this way, or you remove a product, it's going to shift that way. This idea of Q and K is a mathematical version of that perspective. Instead of just saying, hey, they removed something, which way would it go? This is a, let's plug some numbers in and figure out which way it would go. So, then we worked out some problems. We did some rice tables. That was brand new, right? Rice tables? Remember those? Right? Did anyone get hungry while we were talking about rice tables? No. Yes? Yeah. So it stands for reaction. What are the initial values? What are the change values? What are the equilibrium values? The hardest part is usually the change. I don't know why I don't have the other pieces filled in here. Do any of you guys have those two things written down? Because that's bothering me that they're not written in there. What are they? 0.068, 0.047, 0.268. All right, so we figured out those equilibrium values by calculating the change quantity. The change quantity was given in this sentence right here. It says 74% of the oxygen had reacted. That means 74% of the oxygen is gone. It has reacted. So we took the initial amount, subtracted 74% of that value, and found the equilibrium amount. And once I knew how much had reacted, I could apply the 1 to 2 ratio and the 1 to 2 ratio to figure out how much the other values must be based off of that one value. They still have to follow the mole ratios when the reaction occurs. Hey, Mr. Murphy. Yes, Conrad. What are some horrible follow-up questions you could ask about this? I like that. I like that. You're always thinking. This is a molarity, isn't it, Conrad? If it's a molarity, I could easily take it a step further and say, hey, how many moles did you just produce? How many grams is that? It's like your basic back to molarity volume moles stuff. The most common error I see, Mrs. Hoffman sees, Mr. Shangras sees in our world is the switch between can't even write milliliters. That's awesome. That's a problem, but not the one I was discussing. The switch between milliliters and liters. How many milliliters are in 1 liter? 1,000 of these for every one of those. So if you're switching between millis and a liter, you have to move the decimal 3 spots. I regularly see people move it 1 or 2 spots, and then I take 1 or 2 points off of the grade. All right. So that's a very common follow-up question, is just calculating how many moles or how many grams were just produced. I guess I didn't save it. Maybe I saved it while we were doing that problem, because I don't have anything written down here, do I? That's embarrassing. Can I just borrow your paper? Because you write everything down, and you're awesome. I need to clone you. All right. On this problem, we had the initial value spelled out, 1.5000. The tricky thing was this pH value. pH is equal to the negative log of H in terms of molarity. So they've given us 1.98 equals negative log of molarity. How the heck do I figure out that value? Because it would fit right in there. The way you reverse a log is you raise both sides of the equation to the 10 to the, you raise both sides 10 to the whatever. Why am I plugging a negative sign on both sides? Yeah, there's a negative in front of the log. And honest history lesson for you, the whole reason that negative sign is there is because people hate negatives. And the pH scale was not created for the math nerds in the classroom. The pH scale was created for people who can't handle negative numbers, can't handle gigantic numbers. Because what are we doing when we take a log? We're saying, 1.47 times 10 to the minus fifth. And most people's brains just said, no, I refuse to accept that as a number. Times 10 to the minus fifth. I'm never supposed to use scientific notation again after that quiz I was given last week. That's what a lot of people did. So instead, we created a scale to make them easy. Times 10 to the minus fifth, that's going to be like 4.8. Can you handle 4.8 in your head? It's almost the number 5, but not quite. And so they created a scale that people could kind of handle in their head. If I say the pH is 1, most people know that a pH scale of 1, is that dangerous? It's pretty low on the pH scale. That's pretty dangerous. So it's meant to create easy numbers. So we, from this, we now know the amount of hydrogen in the solution. We know the molarity of hydrogen. And then we went from 0 to 0.0105, and we could fill in a lot of the other pieces because this has got to be gaining a quantity. This has got to be gaining the same quantity. Why do these two values have to be the same? The coefficients are both 1. So whatever quantity hydrogen gains, hydrogen sulfite, monohydrogen sulfite is also gaining 1. So they're gaining the same amount. And on the other side, this has got to be losing that quantity because that's a 1. One of the more common issues kids have is they go, you just made 2 things. Shouldn't I be subtracting 2? We're losing one of these molecules. One of these molecules is breaking apart. So we're subtracting 1 value's worth, whatever the value is it's breaking apart. So we're losing 0.0105, which I have this handy paper here. Thank you so much. There we go. Now I have the equilibrium values, and I could calculate K. So K would be the products. I should be using brackets because their molarity. And I've got an equilibrium constant for this dissociation. I'm going to throw an A down there because it's technically an acid. There you go. Thank you so much. And equilibrium constants for acids get a little sub A. We're going to spend a whole later chapter talking about equilibrium constants in acids when they get complicated. This one was not terribly complicated. All right. That one was already filled in. What did I say, though, about this type of question? Let's ease a couple people's minds who weren't here. I had 2 people who weren't here last time. So this problem looks just disgusting. You have initial values, you have no final value, the coefficient's 1, so minus an x, the coefficient's 1, so minus an x, the coefficient's 2, so plus 2x. At equilibrium, we could even write these all in terms of x values, right? We could write, at equilibrium, we're going to lose this quantity. And then we have a constant, we have the equilibrium constant, so we could plug them all into an equation. And then if you really had nothing to do, you could solve for x. Does that look like a fun problem to solve? Okay, the heads went in very 2 different. Some people are like, no, that looks like a disaster. I hated it the first time. And then other people are like, that's my dream. I dream about doing those problems. They're so much fun. I'm not looking at anyone in a striped shirt in the back. But that is not a problem we're going to solve. We're not going to do a question like that. All right? You could go through the quadratic process of solving that, but we're not going to. Mostly because reality hits. Look at the answer, the value of x. How ridiculously tiny is that value? It's insanely tiny, isn't it? What is 0.25 minus this stupid small value? It's still 0.25 because the sig figs eradicates that value, doesn't it? Like, let's take Alex's weight and subtract 1 hair. Not a hair on his head, a hair on his pinky finger. He still weighs the same thing. So, a lot of times these values don't shift as much. What helps us figure out whether or not the x quantity, the amount of shifting, is going to be great or small? What number up there indicates, not the answer, obviously the answer, but what value up there indicates how far a reaction is going to go to the right or towards the left? K. Okay? Right? You can shake your head at that. I'm fine. Yeah, K is, that is the ratio of the products to the reactants. That is a very small value. So you're not going to have a lot of products. You're going to have mostly reactants in order to attain something with such a small negative exponent. You could almost look at that as 1 over 41,000, right? Because it's 4.1 times 10 to the minus 4th. Is that 41,000? 10 to the 4th? So that's almost like it's 1 over 41,000. We're only going to have 1 product for every 41,000ths worth of reactants. That's a tiny amount of products being produced. This is the blank page because it's the break between we start the new stuff. New stuff next? Yay! All right. Let's just eradicate my random little notes there. So, Le Chatelier's principle. Le Chatelier, he's probably French. That sounds like a French name. In Southern Virginia, I think it's pronounced Le Chatelier. But if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce the change. What's that mean? If you add stuff, the reaction's no longer in balance. If the reaction's reversible, it'll shift to undo whatever imbalance you just created. If you add something, it's going to cause it to shift the other direction. And most commonly, people say the reaction will shift this way, the reaction will shift that way. What does that really mean? When someone says shift, they mean this side's going to speed up or that side's going to slow down. Because equilibrium is about the rates, evidently, the rate forward and the rate reverse are supposed to be what? equal at equilibrium. Now, imagine that you have this reaction and it's equal, and then someone comes along and adds in 2. They add in 2. If they add in 2, are you going to have more collisions or fewer collisions between the nitrogen and the oxygen? You're going to have more collisions because there's now more nitrogen. And if there's more collisions, what's going to happen to the reaction rate between nitrogen and oxygen? It's going to temporarily speed up. And if this side is faster, we are no longer at equilibrium, are we? And this side of the reaction is going to speed up temporarily. So I visualize the arrow getting like big in one direction, the same in the other direction. And for a minute, the forward reaction is faster until you get rid of that excess nitrogen and it reaches equilibrium again. So for a second, it's going to shift to the right and get back to equilibrium. All right. Helium is added. There's no impact here. Helium is not in the reaction. It's a noble gas. It's not going to impact any of those things. It wouldn't shift either direction. It's just kind of like getting in the way. But it's going to get in the way of the N2O2 and the NO equally. The container is made larger. All of this is in terms of molarity. Even if you're talking about from a pressure constant, even pressure would have an impact. When you change volume, what happens to pressure? If you make the volume larger, then the pressure would decrease, right? If you change the molarity, you're also changing the molarity when you change the volume. Yeah?
So in this case, that helium wouldn't matter, but if one side has like 2 moles of gas and the other side has 4 moles of gas or something like that, when you added helium, would that change the pressure?
Maybe minutely. A lot of times when you add a noble gas, it gets in the way just as much as it speeds up, because it's causing maybe more collisions per second. But I'm not sure it's a measurable quantity of difference. So. And you'd have to add a lot of helium to really change the pressure. I'll think a little bit more on that, though. So if the container is made larger, you're changing the volume, you're changing the molarity, you're also changing the pressure. However, in this case, in this particular reaction, both sides have how many moles? 2. Let me just write all that down. What is the total reaction order for the top? 2. And the total reaction order for the bottom, 1 and 1, is also 2. Both sides are going to be impacted the same by this volume change. This is kind of weird because I'm starting the very first time we look at this with the one time it doesn't shift. If the amount of products and the amount of reactants have the same total order, 2, 1 and 1 is 2, then we don't see a shift because they'd be impacted equally. If we decrease the container, it'd be impacted equally. Everything would be moving in the same direction proportionally. One of the things that's hardest for people to grasp is everything up here is in the same cylinder. Let's just throw it in that's an eraser. There we go. It's all in the same container together. It's not like the reactants are in one balloon and the products are in a different balloon. They're all bouncing around inside the same container. So when you change the volume, you are making that container bigger or smaller. It's probably a piston, I guess a balloon, but it's all in the same system. And then the last thing we have here is about the temperature. So the system is cooled. When you change the temperature, what changes? We talk about equilibrium. Say again? The constant. So this constant no longer becomes viable. Did we take a second look at that constant, though? That's a ridiculous constant, isn't it? What stands out about that constant that makes it ridiculous? 10 to the 30th, right? It's a pretty big number. So that means that this reaction produces a lot of no's, right? That's a lot of no's and very little N2 or O2 left over. Heavily favors the no. So it says no a lot. This enthalpy, though, is going to help us out. This reaction is endothermic. It gains energy. Whether a reaction's endo or exothermic helps us predict how it would deal with temperature changes in K. When it's endothermic, it takes energy in that direction. We're cooling it down. By putting energy in, it goes that direction. If we're cooling it down, are we putting energy in? No, we're taking energy out. And so what ends up happening, by taking energy out, it actually shifts this direction. What does that imply is happening to the constant if it's shifting towards the left? Yes, the equilibrium constant actually decreases. And so whether a reaction's endo or exothermic can help us predict what would happen to the equilibrium constant. Awesome, I just recorded a hiccup. That's great. All right, hope the home audience enjoyed the sound effect there. All right. Questions about this one? This is a very classic style question about things shifting left or right. I think we should look at 2 more examples. Does that sound good? Or is it 1 more example? 1 more? All right, let's go again. All right. We have the very classic explosive hydrogen plus oxygen makes water. Everything's a gas. It is not actually a very reversible reaction. It probably has a huge equilibrium constant. So, hydrogen and oxygen making water. It's very exothermic, negative 484 kilojoules per mole of reaction. If the water's removed, which way would it shift? So you have K equals H2O squared, H2O2. I left something off. What did I leave off? 2, right? And I'm going to just emphasize something. What are we doing with the hydrogen and the oxygen mathematically? Multiplying them, yes. Yeah, I think I yelled at Austin or something like that last time. Was it you I yelled at? Oh, yeah, it's definitely that guy. Yeah. Multiply them. Don't ever add them. Don't even say it out loud. You multiply the values together. So, in this scenario, water's being generated as it's produced. So let's just pause for a second. Oh, we've reached equilibrium. We have the right amount of products over the reactants. We're in balance. And then Joe comes along and steals your water. Are you in balance anymore? No. So this reaction will now be at Q, not in balance. How are you going to get back to K? Well, these 2 components are going to produce water until you reach K again. So it's going to shift to make products to get rid of those excess reactants, and then evidently he's continuously stealing it. Good job. Right? That's actually conceptually what most chemists are trying to do. Here's a reaction that's in balance, producing something we want. Let's steal that something, and then the reaction will continue to try to reach balance, and let's steal that something that's being produced over and over and over again. All right, we're back at balance. We removed the thief. We've re-achieved balance, and then Conrad comes along and throws in some extra hydrogen. Is it in balance with all that extra hydrogen in there? So again, we're not at K, we're now at Q. With all that extra hydrogen, which do we have to increase and what do we have to decrease? We have to increase the water, we have to increase the oxygen. How are we going to get back into balance? Which way is the reaction going to shift? It's going to shift to the right. Now, I have heard people say, well, I could just add both of these. You could to get it back to balance, but that's not the question. The question is, Conrad throws oxygen in here. How are the other components going to react? Conrad has hydrogen in there. How are the other components going to react? Can oxygen make itself spontaneously from nothing? That would be amazing if it could, but you can't just magically get oxygen. So the reaction shifts to the right, using up some of the hydrogen that is in excess, using up some of the oxygen, and producing water. So what you might have, though, is you may have had, 2, 2, and a million. Add another zero. No, one more zero, right? At equilibrium. And then Conrad threw so much hydrogen in there, 102. It's not in balance, so it's going to shift that way. We're probably going to remove almost every single oxygen that's in there to get back into balance. To get back over there to balance. Back in time. All right. We've re-achieved balance again. The system is cooled. Which way would it shift? First of all, if the temperature of the system's being changed, again, the equilibrium constant's being changed. This is an exo or endothermic reaction. Very exothermic. So it's producing lots of heat. One common thing I suggest kids do is write heat in there. Is heat being made or is heat being used? If it's exothermic, heat is being made. And think of it as a physical thing, even though it's not really. And then you have something you can add or subtract based off of this. The system is being cooled. So someone's coming along and taking your heat, taking that energy out. When this thing is removed, it's not in balance, and the reaction shifts to reproduce that thing, which implies to me what's happening to the equilibrium constant when this reaction is cooled. It shifts that way as it's cooled. The equilibrium constant is oh man, silence out there. The constant must be growing. By cooling it off, it's shifting that direction. The constant's actually growing. Now, weird point of fact, if you remove too much energy, what happens to the activation energy eventually? You might get underneath the activation energy and the reaction just stops because you don't have enough energy to make the components react. So they can kind of work against each other. All right, skipping some stuff. All right, pause for a second. So the other half of equilibrium that we're going to talk about is solubility. And in regular chemistry, here's pretty much how solubility is handled. You look at the here, sound effect. You look at the back of your periodic table, and there's a list of rules, right? And you read the rules, and it's either soluble or insoluble. True? What the heck does that mean? Soluble, insoluble. Insoluble meant doesn't break apart. You see a big solid in there, or you see it floating to the bottom. Good. Usually that's called sinking. Or if something is soluble, that means it dissolves and breaks apart in its ions. Well, this is AP chemistry, so we're going to math the heck out of those two ideas. We're going to take it a step further and kind of go, soluble and insoluble is really an equilibrium situation. If you have too much salt's NaCl. Salt soluble in water? Maybe not. What if I add 5 pounds of salt to 1 teaspoon of water? Right? It actually becomes a math issue. When we say something is soluble, the typical definition is if you create a 1 molar solution, everything dissolves. It's soluble. So if you put 1 mole into 1 liter, does it all dissolve? If, however, you put 1 mole into 1 liter and almost none of it dissolves, we say it's insoluble. And then there's a whole range of slightly soluble, which is really annoying. What do you think slightly soluble means? Some of the mole dissolved, some of it didn't, some minor proportion of it dissolved, and you could tell. Let's jot down a note here somewhere. How would you capture an insoluble solid, something that was not dissolved in water? What's the easiest way to capture something that's not dissolved in water, but there's water around it? They said filtration, people at home, because they're right. Yeah, I'm recording. Good. Yeah, you would pour it through filter paper and capture it, and the water would flow through, right? What if there was stuff dissolved in the water? Would it flow through? If it was dissolved in the water, it does flow through. If it's dissolved, it goes through with the water because it's been broken apart into ridiculously tiny pieces, and they go right through with the water. That's not to say everything goes through, because the filter paper captures some water. Can you grab that filter paper on the shelf back there and bring it up here? Look, Sina, talking to you. You see that filter paper on the back shelf right by the window? Yeah. Is it dry? Just the filter paper. Yeah. All dry? Okay, don't touch the bottom. Yeah, just bring it to me. Bring it to me. So, thanks, man. Hey, can you wash your hands? So when we say something is insoluble in water, like lead chloride, that means that whenever lead and chlorine meet, they bond so tightly together, water can't break them apart. You could dissolve the lead chloride, but you might have to have 75,000 gallons to get a tiny amount to dissolve in, because it's just the ratio is so extreme. Whereas copper chloride is very soluble in water, almost all of it would dissolve. So chemists have created ratios out of this called equilibrium constants, but this constant has an adorable little SP there. The S stands for solubility, the P stands for product. How soluble are the products? We always write the reactions from the same perspective. You have a solid. You have water. And that solid dissolves in water. It becomes aqueous. What would be the the K equation for that? Well, it's already written right there. Let's just pretend we don't see it right there. What would be the expression? Products are copper and chlorine. There's a coefficient of 2. So what happens when there's a coefficient of 2? Squared. That's a solid. What do we replace solids with? 1. So we have copper, I'm right here, copper times chlorine squared over 1 is equal to K. And so we could get a expression in terms of how soluble those products are in water. And then there's a number there. I don't think that number's right. Actually, it could be. Might have looked it up. Even that value looks pretty small though, doesn't it? And that's considered to be a very soluble compound. Lead chloride down here, 3 times 10 to the minus 17th. That value is ridiculously tiny. Does it imply, though, that there is some lead dissolved? It does, yeah. Just a tiny amount. How could you remove lead from your water? Let's say that we're at Alex's house. He serves all of his drinks fully leaded. How could you remove the lead from the water? Or you lived in Flint, Michigan, I guess, too, right? Because that's what's going on up in Flint still a little bit. How do you remove the lead from the water? How do you make it insoluble? If the lead is dissolved in the water, you need some other ion it can react with. The problem in Flint, Michigan is that the water is acidic, and lead dissolves much better in acidic water than it does in basic water. In fact, in basic water it becomes insoluble. So if you change the pH of the water, you can remove the lead. That does create a problem though. You have a pile of lead something building up. You have to then deal with that pile. True? Some of the homes were given filters, so as the lead would go through, it would capture the lead. Really, it's creating a precipitate inside the filter. The filter doesn't work forever because eventually you use up whatever the other anion is that's precipitating out. Good? No, that still doesn't taste good, does it? So they're using a little bit of solubility equilibrium there to figure out how to remove it. Politics. Politics also is involved there. All right, so in your actual notes, this is chapter 16. I think it still says 15, though, doesn't it? Say 15? Yeah, the textbooks shifted this from chapter 13 to chapter 16 when we got new books a couple years back. And I have forgotten to update my notes year after year. So I typically suggest that you set up a rice table in your head for this, but we're going to do it a couple times, just this one time here, and then let's think about some of the implications. Hopefully, how much silver is in your water initially? If you hand me some water, how much silver is probably floating around in boring water? 0. How much sulfur should be in your boring water? 0. Do you agree that hopefully there's no sulfur or silver in your water? In our chemistry life, we're going to assume that all of our water is distilled pure H2O. It's got nothing in it but hydrogens bonded to oxygens and hydrogen bonds keeping them together. And then you come along and you dump that stuff in there. We're going to try to figure out how much would dissolve in using this whole concept of solubility product constants. So some quantity of solid is dumped in. I just put a question mark in for there. A bit of it is going to dissolve. Because it's Ag2S, there's 2 silvers given off. So there's 2 quantities of silver added to the water. And there's 1 sulfur given off, 1 quantity of sulfur added to the water. What would the equilibrium expression look like for that reaction? Let's write the expression down. It would be K, products are silver and sulfur. And I'm making some mistakes up here. Oops, that's a 5, not an S. All right, what mistakes did I just make? It's a solid, so I should really replace the AGS with a 1. Scritchety, scritchety, scratch. Replace that with a 1. What else did I make a mistake on? I made a coefficient error. This is a 2, so this should actually be squared. And then this is about how soluble these products are, so they just squeak a little SP in there. That has no impact on the math. That just tells the person that sees it going, they're measuring how well this stuff dissolves. Oh, okay. That's what's going on. We're talking about dissolving stuff. So we have our KSP expressions equal to silver squared sulfur divided by 1. Well, it looks like the solid doesn't impact the equilibrium constant, does it? So it doesn't matter how much silver sulfide you put in, it doesn't impact the math. Because this could be 75 minus X. It's really to the 0 order. So 75 minus X to the 0 power is 1. It doesn't matter what that value is because solids are always raised to the 0 power. The other 2 values, though, there's going to be some quantity of silver, some quantity of sulfur. We plug a 2x in for the silver and an x in for the sulfur, and that's what's going on right here. What is 2x squared times x? 4x cubed. Cool? And what else did they tell us up here in the problem? They gave us the KSP. That's the equilibrium constant. That constant looks to be pretty small, doesn't it? It's times 10 to the minus 49. 10 to the minus 49. Can you solve for this x quantity with a calculator, not with your head? If you could do it with your head, I'll give you like $1 million. That's how sure I am you can't do it. That's not true, actually. I don't have Anyway, a cube root of 49 would be painful, wouldn't it? No? Conrad is thinking it over now. He's trying to do it in his head. So, should be 16 divided by, this would be 4, and you take a cube. What's a cube root of 4? Ew. Square root of 4, no problem. Cube root of 4. It's not in my head. You pick up a calculator, solve for x. If you know the value for x, what can you do with that value? Plug it back in, and you can figure out how much silver and how much sulfur is in your water. Right? So a German scientist did something similar. He figured out how much gold was in the ocean. The entire ocean. It's a lot of gold. There's more gold floating in the ocean than there is gold in Fort Knox. And he was like, we could just remove the gold from the ocean using precipitation reactions. And then someone pointed out, how are you going to get all of the ocean to go through your machine? And he was like, you win. I was doing like lots of math. He forgot the practical part. The filtering all of the gold, all of the ocean through your machine was completely unpractical. I mean, what's the current that flows through? Come on, people that watched Finding Nemo. Yeah. I mean, maybe you could plant your machine in the current or something like that. Although you would get turtles and you'd feel so bad. You'd be killing so many things. So, that was a weird sidebar. So, because these ideas are always the same, it's always a solid gets dropped into water, some of it dissolves. What you can do is you can say, hey, how many baryons are going to break off of this compound? How many baryons are going to break off of this compound? 1. So there's going to be X quantity of barium in there. How many hydroxides are in that compound? 2. So there's going to be 2x value worth of hydroxide. And so what we can do is, based off of just the equation for the compound, we can write an expression, a math expression in terms of x, that is far easier than actually going through the whole rice table process if it is a simple one compound, boom, that's it, situation. So we have barium would be at x quantity, the hydroxide would be 2x, and I can simplify it in terms of variables. X again is how much dissolves in. KSP is the equilibrium constant. From here, you're pretty much just given 2 possible questions. Let's put a little X here beside D. We're not actually going to do a question like D. We might do with like 1 barium, 2 hydroxides, or 2 ions, or the reverse. So anything like A, B, or C is good to go. But when it gets too complicated, we don't do something like D because it actually doesn't break apart perfectly like that. There's a number of different combinations that might happen. You might have a calcium hold on to 1 phosphate. You might have a phosphate hold on to 2 calciums, and it doesn't break apart as cleanly as the simpler ones like A, B, and C. X is how soluble it is, right? Right? It's how much of the solid dissolves. So in question 2 is actually solving that problem we were setting up. We know the KSP is equal to 4x cubed, which is also equal to 1.6 times 10 to the minus 49th. Silver sulfide has a solubility of 3.4 times 10 to the minus 17th. You plug that value in, and you get the KSP. Or if you divided by 4, you could solve for x, and you'd get the solubility. One leads to the other leads back. So I will either tell you, hey, Zagros, the solubility of the compound is blah. What's the KSP? or reverse that, I'll say, hey Josh, here's the KSP, how soluble is it? Solubility is measured in molarity. What's another way of telling you the molarity instead of just saying, here's the molarity? Giving you, hey, Zagros dissolved 2 moles into 75 liters. It took 75 liters of water to dissolve 2 moles. You got me? It took 75 liters to dissolve 2 moles completely. Now I know the molarity. 2 moles divided by 75 liters. That seems like a small value. It's pretty big compared to this value here. Then you know how soluble it is, and you can calculate the KSP. Cool? Wait, before I go, what's another way of asking that same question? Nadia dissolved 7 grams into an entire pool's worth of water. You could change the grams into moles and then divide by however much water's in the pool. And know the solubility and then the KSP. So in question 3, again we're skipping B. In question 3, I'm giving you the KSP and I'm asking you to calculate the solubility. How much can you get to dissolve? So if you have the KSP value, you write the equation. There's 1 nickel, 1 carbonate. So it'd be nickel times carbonate. They'd be equal values. They'd both be x. So KSP would be equal to x squared. And we solved for how much nickel carbonate will dissolve into the solution. That's me. Evidently that was the best joke I've told all year. So, oops, clear all that off my calculator. So here we have in A and C, we've calculated the solubility. What's that mean? That's the quantity that would dissolve. That's the amount that would dissolve. So let's just imagine for a second that you put 4 grams of lead, is this bromide? Lead bromide into 2 liters of water. And let's just acknowledge the crappiness of those sig figs. 4 and 2, right? So 4 grams into 2 liters. Let's calculate a molarity, right? How do we change? What do we need to do to calculate a molarity? I'm going to walk over here because I don't know that number. Good. So lead is 207. Why did I hit cosine? Lead is 207.2 times 2 bromines, which are 79.9. No, that's a division. Oh, man, I'm glad I'm not taking the stoic test today. So we're going to change 4 grams divided by a molar mass. That's the molar mass, 367, divided by the volume. So 2 divided. So the molarity is 0.005449 if it all dissolves. Is it going to all dissolve? This is, ooh, wait, hold up. What is that value? That's 5 times 10 to the minus 3. This is 1 times 10 to the minus 2. Is that value bigger? This is the maximum amount that will dissolve. Is this value, what was that word? Is this value? Became French for a second, started ignoring letters. Is this value greater than how much they tried to get into there? Yeah. This value, 1 times 10 to the minus 2, is the maximum amount they could get in. This is less than that quantity, isn't it? Did they get it all to dissolve? Yes, they got it all to dissolve. So 4 grams, this is a little bit frightening, 4 grams of lead bromide will in fact dissolve into 2 liters of water. That's disturbing. Anyone want to drink 4 grams of lead bromide? No, you don't. No, that's a toxic level. Interesting. I just grabbed some numbers and I figured I was going to do the opposite. What if we jump that up to 104 grams? How would that change the math? This value would become probably 5 times 10 to the minus 1. I still have it in my calculator. 104 divided by 367 divided by 2. Now it is 1.4 times 10 to the minus 1. Am I going to be able to achieve that molarity? Now, this is the maximum molarity I can achieve for lead bromide. So a lot of this 104 grams is not going to dissolve. Cool? On the opposite end of that, what else could you do? If I said, hey, Andre, you've got 2 liters of water. How much lead bromide can you get to dissolve into that? He knows the maximum molarity. You can say, okay, I know the maximum molarity. Moles, 2 liters. Can I figure out how many moles I can get to dissolve into there and how many grams that would be? And anything above that mass is not going to dissolve. It would be a, what do you call a solid form from 2 solutions mixing? What do you call a solid forming from 2 solutions? A precipitate, yeah, a precipitate. Anything that turns back into a solid or precipitates out. All right, and here's just a solubility question, figuring out how much dissolves, calculating the solubility. All right, common ion effect. What if there's already stuff in your water? Like, why don't we use tap water for a lot of our reactions? There's stuff in it. If I had mixed my lead nitrate using tap water, the lead nitrate would have dissolved, and then the lead would have immediately reacted with the chlorine and the fluorine in our water and made 2 precipitates. It would have been like, dissolve, precipitate, dang it. You can't use tap water because some of the other ions floating around in there. In this situation, we have strontium fluoride that's first just being dissolved in water to make a point. We have the strontium, it's a solid, break apart strontium, fluorine, X amount of strontium, 2X amount of fluorine. Therefore, the mathematical expression would be KSP is times X, 2X squared, simplified to 4X cubed. All right, could you solve for the quantity that dissolves? That's the K. That's the K value. Solve for X. That's the max that should be able to dissolve. Agreed? What if there is already strontium or fluorine in the water? You're not going to be able to get that much to dissolve then. If this equation is assuming 0 plus X, isn't it? Because it's just water. And there's no fluorine in my water, plus 2X amount of fluorine. So in the other 2 scenarios, we're going to say, hey, I've got 0.1 molar strontium or 0.2 molar fluorine. And the strontium and the fluorine are already in the water, and they're going to change the math. They actually end up making the math a lot easier. In A, we just found this is the maximum quantity of X. It can't be bigger than 5.8 times 10 to the minus 4th. If it's any bigger than that, it turns into a solid. If the value for X exceeds that, we start to get a solid. It starts to reverse reaction, starts to precipitate out. In B, there is already some strontium in water. The amount of strontium was 0.1. So I've got 0.1 I wish I had written that the other way around, because that was like 0 plus x, but I've written it this way. Is that okay mathematically that it's x plus 0.1? Yeah, it just bothers me. So there's already some strontium in there. I couldn't get to the pause button fast enough, sorry. What is 0.1 plus the maximum possible quantity? That's the maximum possible quantity. 5.8 times 10 to the minus 4. 0.1 plus the maximum possible quantity is 0.1. How'd it go? All right. So what we can do is we could say x plus 0.1 is pretty much just 0.1 for that one quantity. So I don't have quite the same equation. And we could solve for the amount that would be added to it. It's a ridiculously tiny amount still. With the strontium already in there, we have less that will dissolve in. With the third one, there's already some fluorine in there. There's 0.2 quantity of fluorine. And for the same purpose, we could say, well, 0.2 plus ridiculously tiny is still 0.2. And it just changes the math slightly. It actually simplifies the math down. And so the x quantity gets even smaller. This is called the common ion effect, where you already have an ion in the solution that is in common with what you're trying to dissolve into the water, and it reduces the solubility of that compound you're trying to dissolve into the water. Preguntas estudiantes aquí. It's going to have to be something you have to play with and do the math-wise and think out. I do have some of these questions also on the homework along with the answers to them, so you can kind of like struggle through it, see if you got it right. Also, with every single question, try to kind of go Le Chatelier's with it in your head a little bit. Would it shift that way? Would it shift as far? In A, Le Chatelier's, why does it have to shift to the right? If there's no strontium or fluorine in the water, it has to shift to the right to dissolve a tiny amount of strontium and fluorine. In B, it still has to shift to the right because there is no fluorine already in the water. But since there's strontium, is it going to shift as far? No, it's not going to shift as far in B as it does in A because there's already some strontium in there. And the same thing with C. There's no strontium in our solution C, so it's going to shift to the right. Some of the strontium and fluorine is going to dissolve, but because there's already fluorine in there, it doesn't dissolve as much. And that's what these three answers mean here. How much does it dissolve? A is the maximum amount when it's just in pure distilled water. B and C, we see that that common ion is impeding its ability to dissolve. It can't shift as far to the right. It's a lot of math, isn't it? And that's a beautiful thing. I just bit my tongue. Okay. Not metaphorically either. I think we have the last question, thank goodness. We're talking about solubility, and this looks really complicated. Let me explain. So, I give Lucy and Caroline two solutions. Lucy pours her solution into Caroline's without asking. Caroline gets mad. All right? Not too mad. And we're either going to see a precipitate from these two solutions mixing, or we're not going to see a precipitate. In regular chemistry, we would just pick up the sheet and kind of look and see what's soluble, what's insoluble, and we would do a double replacement reaction. And we would say, here's the one that wouldn't be, right? We would do potassium and nitrate would come together, and sodium and chlorine would come together. And we would check the solubility rules, and we would see potassium nitrate soluble and sodium chloride soluble. No precipitate. What we're going to do here is that same idea, but we're going to math the heck out of it. We're going to turn it into a math problem. We're going to say, okay, the molarity of these things, they would turn into a precipitate if the molarity is higher than, if the solubility product is higher than the equilibrium constant, then the reaction's non-imbalance is going to shift to the left and get rid of some of those ions. So this thing is sodium nitrate soluble. This thing's usually insoluble in water. It would have a 4x cubed expression because there's two silvers. That'd be 2x, one sulfur, 1x. And that is our solubility product constant. This is, I think, the same one we saw earlier in the notes. How did I solve for x? If this is 4x cubed and that's k, how did I solve for x? How do you algebra for x there? I think I just verbed the word algebra. Then I just verbed the word verb. I grammared things a lot. Sorry. If this is the KSP, and that's the algebra expression for the solubility of silver sulfide, do I take a cube root first, or I divide by 4 first? Got to divide both sides by 4 first. Then I cross the 4s out here, and I could take a cube root of both sides. I forgot to mention this earlier. There's 2 very easy ways to take a cube root in your calculator, and there's about 7 ridiculously difficult ways. I think the easiest way is to just take whatever your answer is and go to the 1/3. If you raise anything to the 1/3, that's the same as taking a cube root. Is that what you would do back there? Now you okay. More commonly, a lot of times kids go, math, like number 5 is cube root after you click number 4. I like see how quickly I said number 5, and Andre goes, that's number 4, man. When I need to take a cube root, I go math 4, and then it says cube root. But I just usually raise things to the 1/3 power, so I don't even have to do that. Either way, both of those are easy. I don't know what other way you would do it that makes it harder, but why? Wait just a second. So you've taken your cube root, and now you know the maximum molarity. That's the maximum amount you could get dissolved in the water. And you can look at the values of what's being mixed together and see if you exceed that maximum. If you exceed that maximum, some of it's going to turn into a solid. All right, I got a question. I'm pausing. So Lucy, when you pour your beaker into Caroline's beaker, is the volume the same of your solution now? No, because it's now spread out over the total volume of the two. We would assume that the volumes are additive. If you're adding your 200 milliliters to her 100 milliliters, the total volume is now 300. Technically, it's probably a little bit off. It might be 301 or 299. Some expansion and contraction happens. Let's just ignore that and pretend that the volumes are additive. A lot of times chemists even acknowledge this by saying, assume the volumes are additive, which is to say, we know they're not, but it's close enough. That's not screw up the question and make it harder. So that's what's going on here. Lucy's added silver to your sulfur solution. Lucy's 200 milliliters of 1.3 has now been diluted because of your 100. Here's the molarity of silver. 100 milliliters of sulfur solution has now been diluted to 300. Here's the molarity of sulfur. Do these two molarities exceed the KSP? We can plug those into the expression and solve. I don't know why my voice just cracked there. But we could say 8.67, this is the molarity of the silver, squared times the sulfur. I don't have the math on this on the board. Divided by 1. I'm calculating Q right now. I'm not calculating K. I'm trying to see where the heck we are. If the answer to this is too big, I have too much stuff in the solution, and a lot of it's going to precipitate out. If the answer is smaller than K, I haven't reached equilibrium, and some of it's going to stay in. Let's do some math here. Is it really exciting at home, waiting for me to type into my calculator? Ooh. So here's the answer. My Q value is 2.2 times 10 to the drum roll minus 11. Is that greater than this KSP value? Just a smidge. K was 10 to the minus 49. This is a heck of a lot bigger, isn't it? There is way too much silver and sulfur in the solution, so what's going to happen to that silver and sulfur that's in solution? It's going to rain out of the solution or precipitate down as a solid, most of it, almost all of it, because this value is way too high. And we calculated the max. The max was this, wasn't it? This is the max it should be able to hold. So we can actually look at this from two perspectives, Nick, because you were asking this question. This is the max it should be able to hold. Both of these values are way above the max. Or we could calculate Q. We are way beyond the KSP. We're way beyond how much it should be able to hold. All right, we're going to call it, closing it down. Here's the moment of truth.